it and see, maybe. There you go. All right, so we're in the middle of kind of group 2 here, our type 2 compounds. And again, we want to identify what we're dealing with. We have a metal and a non-metal. And once again, as we've been talking about, that should tell you it's ionic. Always, as I mentioned, whenever a metal's involved, you want to look at it. And that metal is cobalt, which is a transition metal. So that tells you could have a variable charge. So that tells you it's a type 2 situation. So much like we did previously, we want to figure out the charge on that. We have just one cobalt in this case. As we talked about, you will always know the charge on what it's attached to, which is the Cl. That is group number 7, which means it does have a -1 charge. And there are 3 of them based on the subscript that is there. That's going to give us a -3 left over. And that means in this case, our cobalt will have a +3 charge. And that means the name here would be cobalt. Remember, the Roman numeral is for the charge, not how many you have. So cobalt, Roman numeral 3, and chloride in this particular case. Once again, no prefixes, metal involved, so we're not going to do that. And this would obviously be the formula for the cation, and one of these would be the formula for the anion if you needed to write it. For the next one, we see copper, which is a transition metal, and I, which is a non-metal. So once again, that tells you it's ionic. The copper tells you it's a type 2. We'll do our same idea here. Copper, not maybe sure the charge, but I do know for sure I is group 7. And that has a -1 charge, which means the copper here will be going with a +1 charge, again, to balance it out to 0. That's going to give me copper, once again, Roman numeral 1 for the charge, and iodide. Question on that one there. Next, Sn is tin, which is a metal. Br is bromine, which is a non-metal. Again, that's going to tell you it's ionic. Looking at tin, once again, if you look at the periodic table, is not necessarily a transition metal, but it is one of those ones to the right of it, which are named the same way. So that does fall under a type 2 situation. Again, just if it helps you to do so, just draw it out. So we got 1 tin. We have Br, which is group 7, and there are 4 of them. So once again, if you kind of just draw that out, 1, 2, 3, 4, that's a -4. Tin here is going to have a +4 in this case, and that would get me tin Roman numeral 4 and bromide, I think, in this case. Again, the Roman numeral 4 there for our metal, right? Or for our charge on our metal. Any questions on any of those names there? Yeah. Okay, now when we have the name, as maybe a question was earlier, they will, in this case, obviously, when we do see Roman numerals, we'll tell you it's really a type 2. So in this case, we actually don't have to figure out too much. We just want to, again, put it together properly. We know iron is a metal, oxygen is a non-metal, so it's going to be ionic. So iron with a Roman numeral 3 means that my iron has a +3 charge, because that's what the 3 means. So I don't really have to figure it out. It basically will tell me. Oxide is oxygen, which is group 6, and it has a -2 charge. Once again, we want to get to 0, so 6 is the common number there to do that. I could take 3 times 2 is 6. So to get my iron to 6, I would need 1 more, and to get my oxygen to 6, I would need a total of 3. And at this point, you can count it up. That is 2 irons, and 1, 2, 3 oxygens. And then we will get our correct formula in this particular case. Yeah. Any questions on that one there? Looking at the next one, I'm just going to kind of go above, so it might be a little easier to see as best I can. Nickel with a Roman numeral 4 means my nickel has a +4 charge. Chloride is group 7, which means it has a -1 charge. Once again, we do want to get it to 0. So in this case, you hopefully could see you need 1, 2, 3, and 4 of those chlorides to balance out the positive charge. And that means I got 1 nickel and 1, 2, 3, 4 of the chlorides. And there is my formula at that point. Lastly, I have tin Roman numeral 2. So tin, which is SN, is a +2 because of the Roman numeral. And phosphide is group number 5 on the periodic table, which means it has a -3 charge. Again, -3 and +2, common number there is going to be 6. So to get the phosphide to 6, we just need one more. And to get our tin to 6, we need a total of 3 of them, +2, +4, +6. So 3 tins and 2 phosphorus there. SN3P2. Yeah. Any questions on any of those names or formulas? Obviously, you need to be able to go both ways there. Yes. So name to formula, formula to name. Any questions on type 2? So type 2, type 1 are both ionic compounds. And again, the difference is for type 2, because they can make a variable type of charge, we do need the Roman numeral. You don't. So really, obviously, if you're asked any of these questions, really your answer most likely on the page will be either that or something like that. Yeah. But if it helps you to do all the rest so you can figure it out correctly, just do all the rest. What's the difference, right? So if you want to kind of draw it out with the charges, do it that way if it helps you get it correct. But really, obviously, what you need to show on a test or a quiz is basically either give me the correct formula or give me the correct name. You don't necessarily have to show like steps or anything like that. I just do it so it's hopefully easier to understand how you get there. But if it helps you to do it, just do it, right? So you'll have the right answer at the end. Yeah. Other questions? Kyle. All right. So as we talked about here with our ionic compounds, type 1 or type 2, once again, type 1, because they have that fixed positive charge, which is our group 1, 2, and 3, our zinc, cadmium, or silver, we do not need the Roman numeral because no matter what the situation, they will never form any different charge. We again, with our type 2 guys, need the Roman numerals because we need to tell people what the charge is on the particular metal because it can have a variable charge so that everybody's clear as to which one we're dealing with. So why don't you try a couple of those there, see what you come up with. So maybe I'll write a little higher, maybe be easier to see. We have that. We got, actually that one we just did earlier. So why don't we do, a look and see. We'll start with the first one. Hg is mercury, which is a metal. Oxygen is obviously a non-metal. So as we saw earlier, mercury is a transition metal, so we don't know the charge. And oxygen here is obviously group number 6, which means it has a -2 charge. We do know that the charge then on the mercury should be +2. By the way, is this mercury 1 or mercury 2? It is mercury 2 because remember, mercury 1 would also have a 2 on the bottom, right? And also would be a 2 there on the bottom. So this is going to be mercury Roman numeral 2 and oxide like we talked about previously. Here with Ca is a metal and S is a non-metal. Calcium is the metal. Important thing here. That is group number 2, which means it should be a type 1 metal. It has a fixed positive charge. So it should just be at that point calcium and sulfide there for our sulfur. Remember, no Roman numeral is needed as calcium is fixed in its positive charge. Here, lithium and oxygen, metal, non-metal. Once again, we want to always look at the metal, and the lithium here is group number 1, which also means it's a type 1 compound, fixed positive charge. So lithium oxide is all we need. Once again, no prefix for the 2 that's there. Lastly, we have Cr, which is chromium, which is a metal, F, which is a non-metal. So it's ionic. Looking at Cr, that is in the middle of the transition metal region, which means it is going to be a type 2, has a variable charge. So we do want to kind of figure it out. Here we do have group 7 with fluorine. That's F minus. Once again, there are 2 of them. So that's going to give you a -2 overall. That means in this case, our chromium is +2. And that would get us chromium Roman numeral 2, again for the charge. And even though we again have more than one of them, just fluoride at the end of it in this case. Yes? Yes. To use the Roman numeral or not? Yeah. So the thing you want to remember when you're naming, like we talked about earlier, which is it's always the metal that's the most important. And how you could determine basically with the metal, it's going to be, do I need a Roman numeral or do I not need a Roman numeral? And the way you could determine that is if it's type 1 or type 2. So once again, type 1 is basically any metal that is on the periodic table in group 1, 2, or 3. And again, basically for 3, it's aluminum pretty much you're talking about. Or if it's in the transition metal region, zinc, cadmium, or silver. As soon as you see that metal is from one of those 3 groups or one of those other 3, that's a type 1, and automatically you don't have to worry about Roman numerals. You don't have to worry about figuring out the charge. You could just roll right into naming it with the whole name of the metal and then the IDE on the nonmetal. That pretty much leaves anybody outside of that, which is typically type 2. And type 2 metals are typically your transition metals on the periodic table, except for obviously zinc, cadmium, and silver. And just to the right, as we were talking about, where you see things like lead and tin in that area of the periodic table. So if you hit one of those metals in that part of the periodic table, that's where you do need Roman numerals, and that's where you have to, again, sort of figure out the charge. Other questions on that there? All right, here's just a little flow chart again, the kind of what we were just talking about. And again, it's always the metal. Anytime in naming you have a metal, that's really where you should look in terms of naming. And really, again, the decision you have to make, as I just said a second ago, is Roman numeral or no Roman numeral is basically what you have to kind of decide on that. All right, then let's talk about type 3 binary compounds. So type 3 compounds are actually different than type 1 and type 2. These are going to be your molecular compounds, your covalent bonding happening here. So these are going to be 2 nonmetals. Like we talked about with bonding, we're going to have some sharing of electrons. Now, type 3 compounds, which are sharing of electrons, means there's no ions because they're not ionic. So you don't have a positive guy, there's no negative guy. They are absolutely positively the easiest ones to do, but also the ones that people screw up on the most because they think like it can't be that easy. So I'm just going to do some extra things to make it better looking or something like that. This is also the place, as we talked about earlier, that you should never ever use a prefix. This is the time and place for prefixes. Yeah, so this is the situation where you want to use prefixes, and really, again, only the situation you pretty much want to use prefixes for. So when we have a type 3 compound, it contains only nonmetals, and because they're sharing electrons, like I said, there's really no ions. You don't have to figure out anything. This is where we use our prefixes, like mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, maybe nona is 9. Why not a deca for 10? So these are the prefixes, and again, this is the place where you want to basically use them. How do we go about naming these? Well, pretty much the first element in the formula gets named first, the second element goes second. So just like it's written in the formula, you name it. You actually do prefix if necessary. and the first element name. And again, you just use the whole element name on the first one. And then the second one gets a prefix. Bless you. And it's named like everything else we've been doing, which is the nonmetals with the IDE at the end. So prefix on the first one, maybe, and whole name of the first element, prefix on the second one for sure, and IDE ending, just like we've been doing. Now I say maybe prefix on the first one because there are a couple of rules that we want to follow when we're doing these guys. The first rule is we do not use mono on the first name, but it is okay on the second. So we don't use it on the first name, but you can definitely use mono on the second. The other thing that commonly happens, as we will see, is the last letter of the prefix and the first letter of the element will sometimes back up two vowels to each other. So you might end up with an O, or you may end up with an A and an O. And typically speaking, when that occurs, we get rid of the vowel off of the prefix, the first part there. So we drop the kind of vowel from the prefix. So for example, we'll look at CO, right? So C is carbon, which is a nonmetal. O is oxygen, which is also a nonmetal. So as soon as you see that, that should be a very happy time because that is a type 3 situation. You really don't have to figure out anything other than pick the appropriate prefix. So I have one carbon, which the appropriate prefix for one is mono. Should I use that on the first name, though? I don't. So since I'm not going to use it on the first name, we just use the whole element name. So that's carbon. Now I have one of the oxygen, right? And the prefix for one is mono. Can I use that on the second name? I can't. So we go monoxide. And obviously we do not call this monoxide, right? And we have two O's that backed up. So we're going to get rid of the O there on the prefix. And we call this carbon monoxide. Yeah. So we do drop the O and the prefix because we have two O's that backed up to each other. Again, we don't do any like monoxide or anything like that. So again, we want to get rid of that O off of the prefix. So again, two O's that back up, prefix to first letter, drop the prefix vowel or the O, and same thing with A and O. Oddly, two I's in a row seem to be okay. So you could go two I's in a row if you end up with two I's, but really the OO and AO is the ones that you want to kind of watch out for. Again, as you can see here, the second element gets the normal sort of treatment here, IDE on the back end of it. Question on that there. Yeah. An A and an O. AO? Yeah, an A from the prefix and an O from the first letter, like oxygen, right? We get rid of that A off of the prefix. Yeah. Other questions? Yeah. All right, so as I mentioned before, we're going to roll with those. And again, first element always comes first, second one second, and it gets the IDE. Once again, no mono, and there's our prefixes as well. You have a similar table there in your book. Now, as I mentioned, we get a couple of vowels that back up, and again, you can see here, instead of tetraoxide, we do drop that A off of that, and as we just saw there with our mono, we do drop the O off of it to give us a little better thing. Remember, though, that, again, there are certain things that are just by their common name, water, right, H2O, NH3 ammonia, CH4, which is methane. So again, these are the guys that we call by its common name. Now, we talked about it a little earlier, but just to sort of reiterate the point, when we're talking about hydrogen, even though it is a nonmetal, and even though you may have hydrogen attached to another nonmetal, we oftentimes will just sort of name it not really like a type 3. We will name it more like a type 1. So sort of an exception to that is if you had something like HCl, which is a gas, by the way, in this particular example. That is essentially thought of as being like H plus and Cl minus, and we would just call this hydrogen chloride gas, yeah. Even though technically it's two nonmetals, but we kind of think of it more like a type 1 compound. Even if you had more than one hydrogen, like if you had H2S gas, a little hydrogen sulfide gas, which you never want to smell. Well, you might smell it when you go to 1B, but hopefully you don't want to do that. But this would also be basically hydrogen sulfide gas. So that's sort of an exception. Again, that kind of hydrogen is sort of treated more like a type 1 metal, even though it is a non-metal in terms of naming. And again, the 2 is there because sulfur is a -2 and hydrogen basically is a +1. So we need 2 of them. Most of the time when they get out of the gas phase, they go into the liquid phase, which is where, or the aqueous phase, which is where you find that in a solution. These guys become acids, as we'll talk about very shortly. And that's why they're kind of named a little bit like this, more like a type 1 than a non-metal situation that's happening. Any questions on that there? Okay. All right, so why don't you give those a go? I'll give you some names as well. Let's do a little nitrogen tribromide. I'll just make something up. Let's do a little carbon tetrachloride. And let's do let's do something that doesn't exist. Let's do that as well. Trioxygen. And I don't know. Let's go pentasulfide. All right. All right. Names on the left there, formulas on the right. Move these up a little higher so you can maybe see them a little better there. Okay, let's take a look. So I would say, again, out of all the ones that you do, these really should take you like the quickest. But again, this is also the place where sometimes people make a lot of mistakes. So we still want to always sort of start with what are we dealing with. So we look at the first one there. I is a nonmetal, O is a nonmetal. So once again, that should get you to type 3 in your head. And that also should be like, I don't have to worry about anything other than basically just picking the right prefixes of what's there. So I2 means that there's 2 iodines. So the prefix for 2 is di. And again, we use the whole name there of the first element, iodine. 7's prefix is hepta. And oxygen, which is the second element, will get the IDE ending. We will, in this case, drop the A off of the hepta again, so we don't get that A and O backing up. And once again, the second guy does end with the IDE, kind of like normal that we've been doing. Any questions on that one? Here again, the 2 I's are okay. Again, it's mainly OO or AO that you sort of have to worry about. Any questions on that one there? Once again, looking here, C is carbon, nonmetal, O is oxygen, nonmetal. So once again, it tells you type 3. Basically, you can just roll right into the naming, picking the right prefixes. 1 carbon prefix is mono, but again, we are not going to use that on the first name. So we'll just use the whole name of it, which is carbon. Here, 2 for the oxygen prefix is di. And again, it will get the IDE treatment at the end, so carbon dioxide in this particular case. Lastly, we look at P, which is phosphorus, nonmetal, Cl, which is a nonmetal. So again, 2 nonmetals together tells us it's type 3. It is prefixes. We have 1 phosphorus, so no prefix there because we don't use the mono on the first one. So phosphorus, prefix for 3 is tri, and again, second one going to get the IDE treatment at the end. So phosphorus trichloride. Any questions on any of those names? Yeah. Absolutely not. So that's why I say that this really should be the ones that you're done with in like a second, because there's really nothing to figure out other than pick the right prefix. But again, that's what sometimes people try to figure out, and they think about charges, and there's no charges. Again, the situation here is they're actually sharing electrons, so there's actually no ions here. So we don't get any transfer of electrons like we talked about in bonding. So here, because they're sharing, it's covalently bonded. There are no ions really to worry about charges, and that's why we just worry about balancing them out. Yeah. Other questions? All right, then probably the quickest of all is this situation, right? So if you're given a name and you see some prefixes happening, that should tell you it's type 3. And frankly, you just need to write what's there. There's nothing to balance. So di is 2, nitrogen is N, so that's an N2. Tri is 3, Br is bromine. So that is that right there, N2, Br3. Again, nothing to balance because there are no ions in this case. Basically, just need to write what it says. Here we don't see a prefix, but we definitely see a prefix there. And again, as we talked about a lot, prefixes only happen here in this situation, right, with type 3. So we don't have to worry about anything. So carbon with no prefix on the first name means there should only be one of them, right, which is a C. And tetra is 4 and chloride is Cl. So CCl4 would be our formula in this particular case. Lastly, tri and penta, some prefixes. So again, tells me it's type 3. So tri is 3, oxygen is O, and penta is 5, and sulfur is S there, or whatever that is. And then we get O3S5 in this particular case. Yeah. Any questions on type 3? So like I said, probably the easiest ones to do, but unfortunately the one that people do make a lot of mistakes on because of it. Everybody will want to put prefixes on everything else we did previous, but not here. So again, here's the only place really you should have prefixes happening. Any questions on that one there? Yeah. Uh, so say the first part again. So are we talking about two nonmetals or? Oh, I see what you're saying. Yeah. So in this case, you wouldn't do that for this particular case. Again, whatever the formula would be that you get when you do that, you don't have to simplify it. Now, when you talk about ionic compounds, because ionic compounds, when we have the charges, like the positive and negatives, because those are ions, when you put them together, they always should be the simplest, gets you there for the bonding part that we talked about. But it's also because with ionic compounds, like in chapter 8, when you watch that and we talked a little bit about it, when you look at ionic compounds, their molecular formula and their empirical formula, which is the simplest ones, are always the same. And that's why they always should be reduced down in case in an ionic compound. But here, you pretty much is what it is, basically. And you don't have to do the reducing down. Yeah. Other questions? All right. Did those. All right, so again, as we've been talking about, the distinction between type 1, type 2, and type 3. Type 1 and type 2, always metal, non-metal. So again, if you come across a metal and non-metal, that should tell you it's ionic. The next thing you should think about is the metal always, and is it a type 1 metal or type 2? And again, as we've been talking about, what that decision is, Roman numerals or no Roman numerals. Here again, type 3, only prefixes, only has to figure out what's the appropriate prefixes, and clearly no prefixes in type 1 or type 2 situations. Any questions? Little decision tree in case we haven't done that. The next thing we're going to talk about are actually compounds that contain polyatomic ions. Polyatomic ions are weird things in a sense that they are actually groups of nonmetals that are together, which means that they actually will share electrons like we talked about in bonding because they're two nonmetals or more than two nonmetals together. But because of how they are sharing electrons and who they are sharing electrons, they actually end up as becoming an ion. They actually end up with an overall positive charge based on who they're kind of hooked up with and who they're sharing electrons with. So polyatomic ions are weird things that are technically covalently bonded together, but because of the way they're bonded and who they're bonded with, actually does end up with a pretty unequal sharing of electrons and ends up with an overall charge that occurs. So for example, if we take this one here, which is NH4NO3, and I'll just go up here again so it's easier to see, hopefully for you. And in this particular example, we actually have two polyatomic ions present. We actually could split this sort of compound right in the middle. And on the left-hand side, this is really NH4 plus. That one nitrogen and four hydrogens, they are covalently bonded together. They're sharing electrons. And they move around as a whole unit. They never break apart into individual things. If they need to move, they move around. That entire thing has a +1 charge. Now, if you come over here, this nitrogen and three oxygens also are covalently bonded together, and they move around as a unit and has a -1 charge. In fact, we probably drew both of these when we talked about bonding. Just to remind you what we're looking at something like this. They're all sharing electrons here with a +1 charge, and this was our friend I think we drew a couple of times with some resonance structures, but we'll just draw one for this purpose. That is this guy, yeah? So overall, these guys are sharing electrons, but overall, they do end up with a charge, which means it's an ionic compound, essentially, right? We basically have a positive thing and negative thing, which means when we put it together, it needs to equal 0. And that is why when we take this guy that's +1 and this guy that's -1, we put it together and we basically just need one of each of them here in this particular case. Yeah. They are sharing electrons, but it has to do with the electronegativity difference. And there's such a difference in terms of the electronegativity between those elements and how they're bound together that they actually end up with an overall charge that occurs. So for example, something that we don't talk about in this class, but you will talk about in like 1A and stuff like that, is something known as like formal charge. And what that is essentially based on the way these guys are sort of bonded together, is sort of the overall charge that they sort of take in this particular case. So that's one way you could do it, but the actual overall oxidation states, which is another thing you could look at, is in this particular case, this guy actually is carrying around like a -2 overall charge in terms of what's known as oxidation state. Each of those oxygens are basically pulling a -2 that's happening. The oxygen up here is actually also doing a -2 as well. So all those oxygens overall are almost carrying like a -2 charge, because when we look at nitrogen and oxygen on the periodic table, oxygen is further to the right, which means it's more electronegative. So what's happening in this case is all the electrons are heading kind of towards the oxygen, basically. They're kind of moving towards the oxygen and very unequal sharing of electrons, right? Now, the nitrogen actually in this particular case is actually going to end up having a +5 charge because its electrons are actually moving away from it. It's becoming more and more positive in that bond. They're still bonded together. The electrons haven't transferred or anything like that, but those electrons and those bonds are moving further and further to the oxygen, and it's making the nitrogen in the middle more and more positive. And if you add up all that together, -6 and +5, it actually ends up with a -1 charge overall. And it's from that really unequal sharing of electrons. So that's kind of the weird thing about these things is they are actually still sharing electrons, but because of the electronegativity difference and the unequal sharing of electrons that happens, overall it kind of takes on an ion charge and ends up with an overall charge that's going to happen in this case. Yeah. Yeah, so through memorization, you'll know that, but that's how it ends up being, and that's what they always end up being, basically. No, it will always be just like a normal ionic compound, positive guy first, and then negative guy. So just like that, because they're ions, they essentially will come together basically as the ionic compounds do. Always the guy first should be positive, the second one should be negative. But they may not be always +1 and -1, if that's your question. Yeah, so what we will have to figure out is not for the polyatomic ion, because they have fixed charges. So because of the way they're bonded together, they always end up, for example, NO3 minus will always end up as -1, and NH4 there will always end up as +1. That will never change. So they're like locked in terms of the charges of the polyatomic ions. That's why you'll have to memorize them, and memorization is you'll just know, okay, that guy's like -1 or this one's +2. Doesn't matter the situation either. It doesn't matter, who that NO3 minus hooks up with, it will always still be -1. And the same thing with the guy on the left there, the NH4 will always be +1. Doesn't matter who it hooks up with. So that will never change. But it doesn't necessarily mean you always have like a +1 and -1 that will come together. And so, yeah. Other questions? All right, so each of these actually have a specific name. This is what is known as the ammonium ion. And this guy is known as the nitrate, ATE ion. And one of the nice things about polyatomic ions, in addition to what I just said, which is their charges really don't change, they're like always going to be the same, is we always use the whole name of the polyatomic ion. So whatever the name is of the polyatomic ion, it doesn't matter how many you have of them, you will just use the polyatomic ion name. So when we put this guy together, which is essentially +1 and -1, and gives us NH4NO3, we would just use both of the polyatomic ions names, which is ammonium nitrate. And this would be ammonium nitrate. Speaking of ammonium, that should not be confused with what we saw earlier, which is NH3. NH3 with no charge is ammonia. Yeah, so ammonia and ammonium are different things, even though they're related to each other, but they're different things in terms of naming. This is ammonia, no charge. Again, +1 is ammonium, one more hydrogen as well. Yeah, so they are different things. So sometimes people get those confused a lot. First off, any questions on that? Now, because NH4 plus is one of the very few polyatomic ions that are positively charged, most polyatomic ions are negatively charged. So most of them are going to be negatively charged. There's ammonium that's positive. There's like hydronium that's positive. There's only like 2 or 3 that are actually positive sort of ions. So what does that mean? That means probably 99% of the time, if you come across a polyatomic ion, it's going to be negatively charged. And probably 99% of the time, I'll just write it up here. I'll kind of clear this guy out here. We'll take our negatively charged nitrate over here. Probably 99% of the times, like I said, it will be hooked up with a metal. So usually what you will see is a metal with a polyatomic ion. That's probably most of the time what you're going to come across. And as we talked about earlier, when a metal is involved, it is still the most important thing. Yeah. So basically what you typically will do with these polyatomic ions is default back to the question of Roman numerals or no Roman numerals. Is it a type 1 metal? Is it a type 2 metal? The good thing about the polyatomic ion is you're just going to use the whole name anyway, so it doesn't really matter in that guy. So that is probably most of the time that you would see it. So for example, if you had NaNO3, when we look at this, we would break this apart, and that is sodium, which is a metal, and that is a sodium ion with a +1 charge. That is our friend nitrate that we just saw there, which is a polyatomic ion. and that is NO3 minus. Once again, what we're putting together, -1 and +1, that is why when we write the formula, we just need one of each of them, right? +1 minus 1 equals 0. So again, it does need to equal 0 because it's a positive thing and negative thing coming together. At this point, do I need a Roman numeral here with sodium? I don't, because it's a type 1 metal, which means this guy's name here would be sodium nitrate, right? So we just use the whole name. Now, if I had CuNO3 2, right? When I look at this guy, Cu is a metal, right? And again, our NO3 is NO3 minus, which is our polyatomic ion. Once again, metal involved, that is where I'm looking. Do I need Roman numerals with this one? I do, because copper is a transition metal. It's a type 2. So that is a type 2. So what should you do? You should do the same thing we did previously. I know I have a copper that has some type of charge. Once again, once you memorize these here, you will know the actual formula for NO3 is NO3 minus, right? And how many of those NO3 minuses do I have? I do have 2, is what the little 2 there means on the bottom. That means that the overall negative charge, -1 is -2. In this case, the copper should be a +2 to balance it out. So just like we did previously, this would be copper Roman numeral 2 for the charge on the metal. And it does not matter that you have 2 nitrates, it is still nitrate. Again, no prefix here. So 2 nitrates gives you just nitrate. Question on that one. By the way, why did I lay up me some parentheses around that? If I wrote that formula like this, what would I be saying if I wrote CuNO32? I have 32 oxygens, which clearly I don't, right? I got in this case only like 6 of them perhaps, yeah? So whenever you have more than one polyatomic ion, be it the first one or second one, doesn't matter, you do need to put parentheses around it, and the number on the bottom right tells you how many you have so that you do get the right formula in this case. There you go, Jeff.
So is that subscript 2 saying there's 2 NO3s?
That's exactly, it's saying that there's 2 NO3 minuses, yeah. The subscript you're talking, yeah? Yeah, so that's basically, it's basically 2 of these units inside here. And each of those units is basically our nitrate unit, basically. Floating around, truthfully, it'll be floating around in the solution, basically, just kind of floating around as an ion, basically, in the solution. Yeah.
What would be another example of a polyatomic?
We're going to get to a table in just a second, but yeah, there's a lot more, obviously, than just that. Yeah. Other questions? Okay, so let's take a look at that question, which is there just one? That would be great, but there's not. So here's a table from your book. And I also have one up, I think, on Canvas in the, I guess it would be the exam 2 module of a polyatomic ion chart that you could do. Speaking of that, just a reminder as well, I don't know if I said it or not, I also have up there in the exam 2 module, like a table about the geometry for bonding and molecular geometry, kind of the quick way to do polarity and that type of stuff. So if you, I think it says geometry and polarity type thing. So there's like a little chart up there too, if you haven't seen it yet. These are polyatomic ions, and that's, I think, the chart I have up there up on Canvas as well. But let's just take a look at some of these here. And as you can see, a majority of these guys are negatively charged. They all have a specific formula with a specific charge and a specific name. And you do need to know all that here because they make you know everything. So you need to know all that. And more importantly, you do need to know the charges on these guys so that you can put everybody together correctly, right? So you got to kind of know the charges and how to put them together correctly. So how can you do this in a way that will make it maybe a little bit more manageable to try to remember these names? There is sort of patterns to these polyatomic ions that can help you sort of remember the names. For example, if we look, and again, I'll write sort of high up here, NO3 minus that we just saw, which again is 3 oxygens and 1 nitrogen with a -1 charge. That is nitrate, ATE. Now, if you look on that chart, you'll see NO2 minus, which is 1 nitrogen and 2 oxygens, also with a -1 charge. That is nitrite, ITE. If you look on this chart, you'll see SO4 2 minus. That's 1 sulfur, 4 oxygens, has a -2 charge, this guy. That is the sulfate, ATE ion. SO3 2 minus, sulfur and 3 oxygens with a -2 charge is sulfite, ITE. What is the difference between these two groupings here, or these two guys that are in a group? So when you have a group of two, like we do here, they both have a nitrogen, right? They both have a -1 charge, but the difference between these two is the number of oxygens. The first guy has 3 oxygens. Second guy has 2 oxygens. That is the only difference between them, is the number of oxygens. Charge is the same. Number of nitrogens is the same. The one in a grouping of 2 that has the most oxygens will always end in 8. Like you ate too much for the most part, right? So ate too much, the one with the most oxygens. The one in a group of 2 that has the least number of oxygens will actually end in ITE, ITE. So that's why NO3 minus is nitrate and NO2 minus is nitrite. Works the same way here on our guy on the right. They both have 1 sulfur. They both have a -2 charge. Once again here, the difference between them is the number of oxygens. The guy on top there has 4. The guy on the bottom has 3. So the guy on top has the most oxygens. He ends in 8, which is why he's known as sulfate. The one with the least number of oxygens ends in ite, which is why he's known as sulfite. So how should you group these guys together? You should group them together by ones that are related to each other. And you could do one of two things. You could just, remember everything. Yeah. I don't know if you want to do that or not, but you can remember everything. Or you can remember that the idea of 8 is the most oxygen and ite is the least oxygen, which means, let's just say, for example, you remembered all the ones with the 8s, right? If you needed the ite, all you have to do is just take off an oxygen. Everything else is the same. Charge is the same. Everything else is the same. Just remove an oxygen. Or if you remembered all the ites, all you have to do if you need an 8 is just add an oxygen. So you could like remember one of them and know how to adjust it, right? Kind of like drop off an oxygen if you need to go down, add an oxygen if you have the smaller guy, you need to go up. So that's one way to kind of ease the pain of having to remember these, is group them together. And then again, if you want to, like I said, do all the 8s, just know I just need to go 1 less oxygen. Everything else stays the same, to kind of adjust it down to ite if you need it. Now, there's also groupings of 4 that are related to each other. Most common grouping is right here. And I'll flop the page here, maybe find a spot. Oh, yeah, I'll do it right there. So most commonly, one that you see, group of 4, is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. Every single one of these guys has a -1 charge. Yeah, so every single one of them has a -1 charge. They're all moving together. Nobody's breaking apart. The only difference in all of them, as they all have chlorines, right? The only difference is the number of oxygens. On the far left there, we have 4 oxygens, 3 oxygens, 2 oxygens, and 1 oxygen. So in a group of 4, you could kind of break them up into groupings of 2, right? Now, if I go to the right-hand side here, those are the ones that have the least oxygens, right? Which means because they have the least oxygens, they should end in ate or ite. Ite. So this would be like chlorite. This guy would be chlorite. Clearly, you cannot have the same name for 2 different things. So when you have a group of 4 that are related to each other, the one with the least number of oxygens will end in ite, but will also start with hypo. Hypo means less than, basically. So it's the one with the least. So that is known as hypochlorite. The guy next to it, which has 2 oxygens, is known as chlorite. Now, the 2 on the left has the most oxygen, right? They should end in 8. Yeah, so this would be chlorate. This guy would be chlorate. Once again, you can't have the same name, obviously, for 2 different things. So in a grouping of 4 that has the most oxygens, we'll also start with per. So perchlorate, chlorate, chlorite, and hypochlorite. So in a grouping of 4, you got a couple of extra things to put in the names on the most oxygens and least oxygens, but the ending still remains the same, 8 or ite, depending on more or less. Question on that there. By the way, yeah.
So basically what you're saying is that if there's 4 or more oxygens, it'll be per, and if it's 1, it'll be hypo or anything.
It will in most cases. Yeah, in most cases, if you have a grouping of 4, I would say that's probably pretty accurate. Most of the middle ones will be kind of like the 3 and the 2, kind of thing. But yeah, definitely. Now, in this case, that's Cl, right? Which is group 7. That's a halogen. You could actually swap out that halogen for anybody in there. Now, let's just say I had BrO3 minus. Instead of chlorate, that would be bromate, yeah? And if I had BrO2 minus, that would be bromite, right? If I had IO3 minus, that would be iodate, yeah? And if I had IO2 minus, that would be iodite, right? So again, you could kind of swap out in this grouping of 4 any of those halogens, and they're named the same way as well. Question, yeah.
So, previous slide, how come OH minus, it's called hydrogen oxide or hydroxide?
Is called hydroxide, and I'll get there in 1 second. But yeah, any questions on those though? Yeah. So for example, the couple other things that you will notice on this table is if you took something like CO3 2 minus, that's 1 carbon, 3 oxygens with a -2 charge, that's carbonate. Now, if you slapped onto carbonate an H plus, so a couple of things changes if you put that on there. It gets a hydrogen, so HCO3, +1 -2 leaves you a -1 left over. Essentially, what do we put on front of that? We put a hydrogen. So this is sometimes referred to as hydrogen carbonate because we put a hydrogen on front of it. You also will see that with sulfate. If you put a hydrogen in front of sulfate, and again, it's not just a hydrogen, but an H plus, you'll end up with HSO4 minus. Again, the charge does change because it's actually a plus, and that is known as hydrogen sulfate. Now, to further make it wonderful, hydrogen is historically sometimes not used, and this is what is referred to as bicarbonate. Like sodium bicarbonate, a little baking soda, right? For heartburn like you got right about now. This is also sometimes called bisulfate as well. I would say bisulfate, bicarbonate, still very much used a lot in chemistry. So you should really know those names as well because people will go by bicarbonate or bisulfate very, very commonly as well. To answer your question as well, a majority of all these polyatomic ions, as you can see on this list or any of the lists that you look at, will end in ate or ite, but there are a few that actually do end in IDE, kind of like what we have on the periodic table. And the example that you said earlier is an example of that. OH minus is hydroxide, IDE. There's also CN minus, which is cyanide. There's N3 minus, which is azide. So there are a few polyatomic ions that end in IDE, but a vast majority of them will end in ate or ite. So there's just a few that she has to kind of worry about. Also, as you can see from this list as well, NH4 plus again is probably your most common polyatomic ion that you come across. Technically, H3O plus is another one. That is what is known as the hydronium ion. But outside of that, most of them, as you can see here, are going to be negative. So, yeah.
Valid though, hydrogen is the second element, but it's placed in first, it's named first.
It has more to do with that's really what the major component of a base is, OH minus, and that's known as hydroxide. And that's really the way it's named. It's sort of like a special name for it because of that reason. Just like H3O plus, which is the hydronium ion, is also sometimes referred to as the hydrogen ion, when it's just H plus as well. They're like the same thing. So some of these things do have some names that just like historically, people call it that and type stuff. Yeah. And it doesn't go strictly, in this case, polyatomic ions by like non-metal sort of naming. They just were named those things, and that's just sort of the name that is stuck with it as well. So even though they are technically non-metals together, they really don't necessarily follow type 3 naming because of that. Other questions? Now, for example, if you had PO4 3 minus, right? That is phosphate, right? What would PO3 3 minus be then? It would be, right? So I know this is the 8, so ite should be one less oxygen, which is the only difference there, right? Everything else is the same. Both have one phosphorus, both have a -3 charge. It would be phosphite, right? What would hypophosphite be? Well, yeah, we just keep dropping off one oxygen at a time, right? 3 minus, right? What would perphosphate be? Yeah, PO5 3 minus. Again, nothing changes. So this is the way, like I was saying, if you just remember one of them and know how to adjust, you probably will in most cases get the right answer. They don't always work perfectly like that, but most will work kind of perfectly like that. Definitely for our classes and stuff like that, you'd probably be in pretty good shape. So again, like I said, if you want to learn the 8s and just know, okay, if I need an ite, just take off one oxygen at a time. If I need a hypo, take off one more oxygen, right? Or if I need a per, add an oxygen type of thing, and you usually will be in pretty good shape. Any questions on that there? All right, so let's talk about, like I said, they basically are attached with metals or non-metals. Let's try some here. Why don't you name some of these here? I'll leave the chart up for now. Obviously, here you need to know these names and stuff. So you do need to know the names of the polyatomic ions, which is on this table. And also, again, obviously the charges to go with it, like we talked about, so that you can properly do everything. All right, so let's do some names for some formulas here. Let's do, I don't know, let's do FeSO4. Let's do MgHCO3 2. Let's do CuOH2. Then why don't you also write the formula for, let's do potassium hypochlorite. Let's do nickel for cyanide. And let's do lithium dichromate. All right, so obviously names for the ones that have formulas and formulas for the ones that have names. See what you come up with here. injury report about, you're not doing a lab. All right, so let's take a look and see how we're do some of these. I'm gonna rewrite it here so you can write it a little bit higher so you can see it hopefully a little bit better. All right, so in this case, what we want to do is think about again what we got going on. So we obviously have a metal, and hopefully at some point soon you'll recognize that as a polyatomic ion. So this is again a metal and a polyatomic ion. Once again, it is the metal that's the most important. In this case, that's magnesium, which means it is a type 1 metal. This is group number 2, so we don't need any Roman numerals. So really, it's the same sort of ending for this, which is because that's a type 1 metal, you actually could just go right into the naming. So we're going to use our whole name of the metal. And just like we talked about, we will use our whole name here of our polyatomic ion. In this case, you could write hydrogen carbonate from that list. Or again, this one is sometimes referred to again as bicarbonate instead of the hydrogen essentially is sometimes used. And it could be called magnesium bicarbonate if you like as well. The idea here with the formula is we have a magnesium that's group 2 plus 2. From that table, that is HOC3 minus. I said that really bad, HCO3 minus. And again, we have a -1 and a +2. That is why we need 2 of those guys, and also why we have parentheses around it and a 2 on the bottom. Again, ultimately, it is an ionic compound. We're just going to balance out the charge to 0, which is really how we got there. Question on that one there. Yeah. You do not, again, because the magnesium is group number 2, which means it has a fixed positive charge. So it falls under that type 1 classification where you don't need Roman numerals. Other questions? Yeah.
Just to clarify, so that 2, the subscript 2, not only just for the element in the parentheses, but the other one as well? Go to both elements?
No, it goes for whatever's in the parentheses only.
Oh, only.
Yeah. So this 2 goes for whatever's inside the parentheses. Yeah. It has no effect on it. If there was like an extra magnesium, there would be a subscript here written before it. Yeah. Other questions? All right, so taking a look at the next one you had, which was FeSO4. Once again, metal and polyatomic ion. Always metal involved. We're going to roll with what's going on with that. That is a transition metal, which as we saw before is a type 2, which means we do need Roman numerals here. So again, we're just going to go at it the same way. I don't know perhaps my charge, but once I memorize my polyatomic ions, I know that SO4 is carrying around a -2 charge. And again, to balance it out to 0, I would need a +2 in this situation to balance it out. And that would give me my name here, which is iron. Once again, we do need the Roman numerals because it is a transition metal and has a variable charge. And again, we just use the whole name of our polyatomic ion. Does not matter how many polyatomic ions you have, you just use the name. So iron 2 sulfate in this case. Any questions on that one there? Next is CuOH2, and again, copper metal, polyatomic ion. Once again, copper being a transition metal, so again, going to tell us it's type 2. We need to figure out the charge. Here with the parentheses around the OH tells us OH is OH minus, and there are 2 of them in this case. That gives you a -1, -2 charge. That means to balance it out to 0 here, copper will be a +2 in this case. And this would be copper Roman numeral 2 for the charge on the metal. And once again, even though we have 2 of these hydroxides, it does not affect the name. We just use the whole name of the polyatomic ion. So copper 2 hydroxide. So much like how we use just like the whole name of the IDE, we don't put any prefixes. Again, no prefixes here. The easiest way to remember that, as I said earlier, I have a metal involved. I should not be using a prefix. So that is just the way you can remember. It's super easy. Metal there, don't prefix it. Yeah. Question on any of those names there are formulas. Names, I guess it would be. Yeah. All right, then let's take a look at the formulas ones here. So we had potassium, and I went with hypochlorite. So once again, we're just going to remember we see a polyatomic ion, so it should tell you it's ionic. So that will tell you, I just need the ions. So potassium is group 1, so that's a K+. Hypochlorite is ClO-. Once again, that entire thing has a -1 charge. So ultimately, we're putting +1 and -1 together, which means we just put it together, basically, and we will end up with KClO in this particular case. Any questions on that one there? Next one is nickel 4 cyanide, right? Again, polyatomic ion tells us it's ionic. Just like we did previously, nickel with a Roman numeral 4 means this guy has a +4 charge. So again, it tells us that. Cyanide is Cn-. Once again, putting it together to equal 0, we would need definitely more of the CNs. So a grand total of 4 will do that for us, giving us a formula of 1 nickel and 1, 2, 3, 4 of those polyatomic ions. Since I have more than one, I need a parentheses and a 4 on the bottom. So again, we can't go NiCN4, right? So that would be just 4 nitrogens, not the carbon as well. Question on that one there. Lastly here, lithium dichromate. All right. Metal polyatomic ion. So lithium is group 1 +1. Dichromate is Cr2O7, maybe a 2-. It's been a while, but I think that seems right. There you go. And in this case, that entire thing has a -2 charge. That has a +1 charge. To balance it out to 0, we need one more lithium. That's going to give us 1, 2 lithiums and one of these guys. If you have just one polyatomic ion, you really don't need parentheses around it. Now, earlier I said that you will never do a prefix with a metal, except in one situation. This would be an example of that situation. The die here is not because we put it on, but the die is part of the actual name of the polyatomic ion. So that is the only time you will actually see a prefix kind of with a metal, and it's really just because the polyatomic ion's name has an actual prefix like dichromate. There's a few of them on those tables there. Dihydrogen phosphate. So there are a few that actually do have prefixes in their name. And again, that would be the only time you would ever see like a prefix and a metal together. And again, it's more so it's just the name of the actual polyatomic ion. Question on polyatomic ions, naming them, writing the formulas. The sad answer here is yes, you do need to know them, the names and the formulas. But again, you do want to group them like we talked about. And I think that's really the best way to do it is just pick whichever one you want to remember and then just know how to maybe adjust it up or down depending on what you need in terms of just changing the oxygen. Again, it's just the oxygen change. Everything else stays the same. Charges stays the same. Nothing else will ever vary on this. Any questions on that there? And again, this chart should be up on Canvas in that exam 2 module, okay? As well. All right. Last thing for naming after we take a look at these patterns that we talked about. So we'll just kind of go through those here. All right, well, we kind of did those already. Put hydrogen in front. All right. Again, I'll just scroll through in case you want to look at it again, but it's pretty much everything we just talked about. Last thing we're going to talk about is naming acids. And when we name acids, acids are basically substances that produce H+ ions in solution. So for something to be an acid, it has to have the ability to, in solution, pretty much let go of some H+ and allow a bunch of free H+ flying around. As you'll learn about when we talk about acids and bases in a later chapter, H+ and a polyatomic ion, H3O+, which is the hydronium ion, are essentially the same thing in acid-base chemistry. They're used sort of interchangeable with each other, the hydronium ion and the hydrogen ion. But that's basically what makes something an acid, is that ability to not hold on to its H plus, but actually let it go into solution and be free, basically. Now, the cation, and we think of acids as being like ionic because when they go for in solution, they essentially break apart. They're electrolytes, so they'll release these things. The cation for all acids are H plus. So H plus is always the positive guy here for any acid. And that's really the H plus is going to come off. So the anion is how you get the rest of the name. And it really determines, in terms of the anion, basically, is there oxygen or is there not oxygen? That's basically the question you want to ask when you're going to name acids is there oxygen or is there no oxygen? So let's just talk about how you go about doing that. If you're looking at an acid, the first question is no oxygen involved. So if you look at an acid and there's no oxygen involved, basically your acid will start with hydro something ic acid. So for example, HCl, that has no oxygen involved and that is an acid. So this would be hydro. The middle part of the name comes from the negative guy. So that's like chlorine or chloride. So this would be hydrochloric acid. It's from the negative guy. The cation here is H plus. The anion is Cl minus. Yeah. If I had HBr, no oxygen, so this would be hydrobromic acid. Now you may be saying to yourself, didn't we just a second ago call this guy hydrogen chloride? And the answer is yeah, it's a gas in that case, and it is called hydrogen chloride. But when you take it and you bubble it through water, you get AQ next to it, which is aqueous, a water environment. And you get an acid, basically. Yeah. So acids will always have this aqueous symbol next to it, or should really, if you're writing it, always have the aqueous symbol next to it. That way you know you're dealing with the acid, basically. And it will be named hydrochloric acid rather than hydrogen chloride. Hydrogen chloride is typically a gas. Yeah, a G there. So it's typically a gas. And an acid should be aqueous because it's always in solution, and that's what makes it an acid is when it goes for a swim, it just breaks apart basically and gives off that H plus. Yes, sir.
Speaking about solutions, is it only water or is it any?
So the definition of solution is really, it's basically a mixture is what a solution is. It's a homogeneous mixture. So it has two parts. It's what's known as a solute and a solvent. Solvent's the larger part. Solute's what's usually dissolved in it. And water oftentimes is the solvent, but it doesn't always have to be the solvent. So, but in a lot of cases with ionic compounds and things like this, water is a really good solvent for reasons we'll talk about in a later chapter. But like, for example, if you had NaCl, the solute, which is the smaller part of the solution, the stuff dissolved is sodium chloride, probably a solid. And the solvent in this case would be water. In this case, and the salt will dissolve in the water basically and make a homogeneous solution, which is basically a homogeneous mixture. It looks the same throughout, right? You can't see the salt water. That's what that is, yeah. Other questions? By the way, again, H plus is the cation, Br minus again is the anion in this particular case. So if your acid does not have oxygen, hydro something ic acid, middle part, the negative guy's name basically fills in the negative part along the way. Now, if you have, let's get here, I'll find somewhere to write maybe come back here. All right. up here. Now, if your acid does have oxygen, so the answer is yes to the oxygen, it will contain one of everybody's favorite things that we just saw, a polyatomic ion. And as we just saw, for the most part, those polyatomic ions end in either ate or ite, as we just saw. And if your acid does have oxygen and your polyatomic ion ends in ate, your acid name is something ick acid. As I might have said earlier, I ate too much, I feel icky, is a good way to remember that, right? So if you have something like HNO3 aqueous, NO3 is nitrate and it has oxygen, so this becomes nitric acid, yeah, based off of nitrate, ATE, nitric acid. If I had H2SO4, which is aqueous, that has oxygen, that is sulfate, which means my acid would be sulfuric acid. Again, ATEIC at the end. By the way, again, in this case, the cation for this guy is H+. The anion is NO3 minus. For this guy, the cation is H+. The anion in this case is SO4 2 minus. That is why we have how many H pluses there? 2 of them to balance it out, right? Because this guy has a -2 charge. That is why we need 2 of these guys to balance out that -2 charge. So acids, because they're aqueous, they're thought of as being ions. You still need to balance out the charge with hydrogen. So that is why, again, we have 2 of them there in that case. Also why we just have 1 here in this case, right? +1 and -1, again, gets you to 0, which is what you need. So if you do have oxygen, it will contain a polyatomic ion. And if that polyatomic ion ends in ate, then your acid is something ick acid. If your polyatomic ion ends in ite, and it does have oxygen, it'll be something OUS acid, like HNO2. HNO2, that is nitrite, ITE. This will then become nitrous acid. Yeah. H2SO3. SO3 is sulfite. This will be sulfurous acid. So OUS for somebody that ends in ite, IC for somebody that ends in ate. Is there hydro in this situation on either of those? There is no hydro to begin with, yes? So if you have oxygen and you're naming an acid, you should not use hydro, yeah? Hydro is only for acids that do not have oxygen. Like we saw earlier, the HCl, the HBr, those guys. Any questions on that there? All right, so here's some examples of acids with no oxygen. So HF is hydrofluoric acid, no oxygen, hydroic acid. HCl, as we saw, hydrochloric acid, hydrobromic acid, hydroiodic acid, even H2S, hydrosulfuric acid. Again, hydro to begin with, ic, middle guy going to be the negative in this particular case. Here again are some guys that do contain oxygen. So nitrate, ic, nitrite, ITE, OUS, sulfate, ic, sulfite, OUS, phosphate, ic, and that's acetate, acetic acid. Yeah. So that is the way you go about naming acids. Bases are named the same way. A lot of strong bases have hydroxide in it. So it's named like a polyatomic ion with hydroxide, basically, like sodium hydroxide, potassium hydroxide, calcium hydroxide. So a lot of the strong bases come from group 1 and 2 on the periodic table, but strong bases are pretty much hooked up with your polyatomic ion hydroxide, and you would just name it like you would do in a polyatomic ion, basically, in that particular case. Question on nomenclature, now that you are professionals. So HF is hydrofluoric acid, right? As again, we have no oxygen. HNO3, as we saw there, is nitric acid. All right, any questions on naming? Yes. Say it one more time. Which one?
An acid that has chlorine in it.
Yeah, one of those, like one with a 4. Yeah, so for example, why don't you give this a try? What would you call this acid? What would you call this acid? Why don't you give it a try first, both of those? And we'll add one more to the list. Why not? We'll do this guy as well. All right, so for all 3 of these acids, what are the name? And what is the cation and anion in each of them? Write the formula for each of them. Look, we'll start here with the first one. So this is an acid. I see a hydrogen, and I also see aqueous next to it, so it's a good sign that's an acid. I see oxygen as well, so I'm wanting to look for my polyatomic ion, which would be this guy. That's going to be BrO3 minus. And we also know that always our cation is H plus, right, in this case. So for all acids, that is our cation. And that is our anion in this case, right? So that is bromate, right? And that would then mean that this is bromic acid in this case, right? Again, no hydro in the front here because it does have oxygen. It ends in 8, so our acid should end in ic in this case. Question on that one there. Yeah.
Like go back with the chart and see where, like the polyatomic chart.
You would. So that's where I got that from. Yeah, so that's where that came from. And it wouldn't be, again, this would be one of those ones, again, it wouldn't necessarily wouldn't be on that chart, but it is related to the ClO3 minus, which is chlorate. So since we substituted that in, like we talked about with the Br, that one guy came bromate. But again, in terms of the acid, it does end in 8, which is the important part of it, and that gets you to the ic for the acid part. Yeah. Other questions? All right, same thing here. Looking at that, that's an acid, got a hydrogen, got an aqueous type of situation happening here. So that is H plus for my cation for that guy. ClO4 minus, going back to that chart to find it, and that would be perchlorate. Yeah. Once again, it does end in 8, which means that my polyatomic ion or my acid should end in ic. We actually do keep the per part here. So this is what is known as perchloric acid. So you do need to keep the per in front of that, by the way. And again, it becomes perchloric acid in this particular case. Any questions on that one there? Lastly, up here, that's an H, that's aqueous, so that's an acid. H plus, that is ClO minus as my anion. That's my cation here. ClO minus is hypochlorite. That ends in ite, which means my acid should end in OUS, right? So ite to OUS. So we do also on this one need to keep that part of the polyatomic ion name. And this guy up here on top, which I'll circle, will become, actually, I just erase something here. I'll do it something this way. That would then become hypochlorous acid, yeah? So OUS and the hypo does still stay here. Any questions on that one there? Okay. That is all the naming I got for you today, I think. Any questions?